another professor. So then
one more is come, huh?
One more, sir.
Who?
Vijay Ramnath from Sai Engineering College.
Okay. How many papers are there in this, sir? May I know who's coordinating?
Nine papers, sir.
9 papers. May I know who's coordinating?
Sir, this is Prem Kumar.
Prem Kumar, okay.
Yes, sir. Assistant Professor Mechanics.
Okay, sir.
என்ற குழப்பத்தில் இருக்கும் பக்தர்களுக்கு ஓர் அரிய வாய்ப்பு. வழக்கம் போல் மாலை அணிந்து விரதம் மேற்கொண்டு அம்பத்தூர் செங்குன்றம் சாலையில் கள்ளிக்குப்பம் சண்முகபுரம் உடலில் எதிரில் அமைந்துள்ள நமது அம்பத்தூர் சபரிமலைக்கு வாருங்கள். நமது ஆலயத்தில் இருமுடி கட்டிக்கொண்டு கடுத்த சுவாமி தரிசனம், கருப்பண்ண சுவாமி தரிசனம், 18ஆம் படிகள் ஏறி கொடிமர தரிசனம், கணபதி தரிசனம், முருகன் தரிசனம், நவகிரக சுற்று, மாளிகைபுரம் தரிசனம், நாகராஜ சுவாமி தரிசனம் செய்து கொண்டு ஐயனை தரிசித்து நெய்யபிஷேகம் செய்து ஐயனின் பூரண அருளை பெற்று செல்லுமாறு கேட்டுக்கொள்கின்றோம். அனைவரும் முகக்கவசம் அணிந்து சமூக இடைவெளியை கடைபிடித்து இருமுடி செலுத்தி நேர்த்திக் கடனை நிவர்த்தி செய்து நெய்யபிஷேகம் முடித்து ஐயனின் அருளை பெற்று செல்லுமாறு கேட்டுக்கொள்கின்றோம். சுவாமியே சரணமையப்பா.
Sir, I think.
Yes, sir.
Sir, I think we can start now, sir, because I am late. So we'll start. Good morning, one and all. This is Prem Kumar, Assistant Professor from Mechanical Engineering Department. I welcome for the 3rd International Conference on Materials Manufacturing Mechanical Engineering for Sustainable Development. So in 2020, so this for this particular gathering, and our chairperson sir will be interrogating with your papers which you are presenting. We'll start with Mr. Vignesh sir. Sir, Vignesh sir, is there?
Yes, sir. I'm here, sir.
Okay, sir. Your title of the paper is Usage of Insulated Refractory Castable Corners for Making Jointless Bangles, right, sir?
Yes, sir.
Can you please present in front of our chairperson, sir?
Yes, sir. I'll share my screen right now.
Sir, you can take your papers.
Okay.
So, Prem, sir, is it? Can you all see the screen, sir?
Yes. No.
Yes,
not
of
yet.
course.
I could not.
No, that is. You are. I think you are. I mean, you must in full screen. You have been.
Yes. Now
I am getting it. Now. Yes, sir. Now I am getting it. Now we are getting it.
I am not getting it, sir.
Sir, Kisumut sir, you are getting it, sir?
No, I am not getting it. That's what.
Sir, again, please kindly share it, sir.
So I've shared my screen again.
Yes, sir. Sure.
Is it okay, sir? Can I start, sir?
I could not see anything in your
Okay, sir. Maybe it's the net problem. I'm not sure.
You at least.
Okay, sir. Mr. Next
Vignesh.
person.
Yes, sir.
Vignesh,
Yes, sir.
Yes, yes.
you just show. I couldn't see the windows.
Maybe I've shared it like 3 times. Sir, this is this screen, sir. Can you able to see it now, sir?
Oh, I didn't get. So
Okay.
anyway, are you people able to see me?
Yes,
Sir,
sir.
there are
We can
sir,
see.
sir, there are two Vignesh. This thing kindly pin into Vignesh presentation. I think you will be able to see.
Into Vignesh presentation.
There are two names by Vignesh.
The one is the presentation and one is for myself.
Okay, your presentation to anyone is like that. So only
Yeah.
my
Okay.
presentation is coming, sir.
Sir,
Sir,
is
pin
it
to
And now it is coming, sir. Yes.
yeah,
okay?
yeah.
Usage of insulated refractory castable furnace. Okay.
So can I start?
Okay, sir. Please proceed.
Good afternoon, everybody. My name is Vignesh, and I'm an assistant professor working in Sri Krishna College of Engineering and Technology, Coimbatore. And I'll be presenting my topic on usage of insulated refractory castable furnaces for making jointless bangles. So I've done this study along with Dr. M.R. Ravi from IIT Delhi. So these are the contents that I will be presenting to you today. So it starts with an introduction to the whole process. I will also talk about the layers inside the furnace which we are trying to design, the workflow that I have followed, the field visits which gave me an idea of how to select the materials, the testing which was basically an analytical testing as well as the physical testing. A small physical test was also done to it, and I've concluded with some pointers. So the introduction, so I'll just move this. Introduction is like the bangles are used in all these wedding ceremonies, which are really traditional, which are considered to be really traditional in the northern part. And northern part, they have done jointless bangles, which is requiring more skill compared to jointed bangles that we see every day. So this is made up of glass. So the problem with this is it requires more amount of skill. Along with the skill, it has a couple of difficulties in terms of temperature which comes out of the furnace, and also the gases that they inhale from the process which comes out of the furnace. So that those two things were really hampering the efficiency as well as the efficiency of the artisans who make the glass bangles. So Rutag is a body in IIT Delhi identified this particular problem, and they also came up with a solution for making the life of the artisan a little better. So they came up with this solution called a furnace, 4-layered furnace, which is used to make the bangles, but the furnace will not let the high temperatures to come out of the whole apparatus, and also the flue gases will not be coming into the or it won't they won't inhale it. So that's the whole idea. They have done it with 4 layers, as you see in this photograph that I've given in the right hand side. So the 4 layers consist of these things. Insulation blanket was the first and the third layer. The refractory castable concrete was considered to be the second layer. It's actually concrete. So the fourth layer was steel casing, which housed the whole apparatus. So if you go back and see this photograph, the firing will have a temperature about 1300 degrees Celsius, and the insulation blanket was fixed as the first and the third layer. The castable concrete was the second, and the fourth one is the steel casing. And you see the temperatures which we wanted to have. This firing will have a very massive temperature. So if we don't really give a very good insulation or a refractory castable concrete to resist this high temperature from coming out of the furnace, then it's very difficult for the artisans to make their art. So that's what we wanted to do. The flow chart which I wanted to present was like, we went to a couple of sites before this, and we decided how to select the materials based upon what was built before it. See, this furnace that you see over here, in which the artisan is working, is not. It's not just the first iteration or the second iteration. There was multiple iterations before this, and then they came up with this solution. So we wanted to go back again and see what happened in the earlier versions of the furnace. That's the first idea. We have a literature review which was done, which was the iterations which was made, and then we started and we selected the materials. We did the analytical testing, physical testing, and I will discuss the design and discussions right now. So, so the first thing which I talked about was the field visit with to Purampur. Purampur is a village in Haryana. So IIT Delhi, along with its professors, came up with this solution for making pottery books and all that. The problem with this was it was made up of natural materials. Natural materials did not have the capacity to resist high temperatures, and this resulted in cracks over the walls that you see over here. So in order to reduce the cracks, they came up with another solution to fix steel wires all around. But that again proved to be a vital mistake that they did, because we have studied in a temperature loading that if we don't disturb anything, if the material is free to expand or contract, there is no stress on it. But if we restrain something, if we put a fixed end on both sides, then there's something which will come out of this, the stresses which come out of that. So natural materials was not a very good option, and also this was the second furnace which they made. It was made up of rad brick bond, which you see over here, and it was actually good, better than the first iteration. But the thing is, it could not sustain the temperature. The temperature was not sustained, so that it required more amount of fuel. It reduced in its efficiency. Therefore, the one thing which we learned from these two furnaces was, like, natural materials alone cannot be used for making this furnace, because as you all see, it did not have the capacity to withstand the higher temperatures, and also to withstand the temperature at a constant level, steady state. So that's why we selected the materials based upon these parameters, which are called refractoriness, and PLC, which is like the deformation. PLC is like a permanent linear change, and these two parameters were essential in selecting the materials. Right? So as I said before, we had four layers, among which one was the insulation, the second layer was the refractory castable concrete. So in order to do that, we shortlisted Whiteate and Serachim blanket as as the refractory castable and the insulation respectively, because they had a very good refractoriness value, and also the PLC was little bit lesser. Okay, that's why we have chosen these two materials. As a civil engineer by trade, I always, I'm a civil engineer. When I think about concrete, I always think about the strength. Here, surprisingly, we did not even talk about the strength at all. The only thing which we wanted to do was it should withstand the temperatures coming onto the structure, and also the strength wise, it had a sufficient amount of strength, but that was not taken into account over here. That was a little surprising for me as a civil engineer. Right, so this was the testing which was done. This was done in StatPro, which is like the civil engineering software used for analysis and designing purposes. So the middle picture shows you the geometry, and the left hand side shows you the 3D rendering view. Those openings that you see over here are used for the melting of the glass, and they can take it out for facilitating the whole process. So the values that we entered into STAT was given is given in the last picture over there. And the main thing which we wanted to find out was whether we require any amount of reinforcement. So all of you guys are living in RC structures. It has steel inside it. It has steel inside concrete. But when you come up, when I went to IIT, they asked me if I needed to design, or if it is required for steel to be included along with the concrete. So the thing is, the structure looks very awkward. As a civil engineer, we don't really build all these complex structures. We do, but it will be like steel or concrete. It won't be mixed together, right? So this was a complex structure, and it was not practically feasible to provide reinforcement. But I was assigned to check if the reinforcement was required or not. And this was the loading which was given, the temperature loading which was given in the middle picture. Okay, that was given, and as expected, the openings were the weakest positions or weakest parts of the whole structure, but all the other parts were really strong enough to withstand the temperature loading. That was the thing which we got. And one more thing which we need to note here is that this structure is analytically speaking, it was subjected to this temperature loading directly. There was no insulation in the first layer or third layer. It was subjected to temperature loading directly. So it was like the worst case scenario, and it came up with a good and it came to be good. The results were not really bad at all, and we decided that we don't really require any reinforcement for these structures. That was the first one. The second one was a physical testing which was done for the for the refractory castable. So when you think about concrete, we have to have water, we have to have cement, coarse aggregate, fine aggregate. We need to mix it up and pour water into it. So when we got the castable from the guy who sells it, it was like a mix, a dry mix. So you just needed to add water to it, and you get this really good mix that you see in the first photograph, in the mold. I mean. So 11% of water was added to it, and we kept it inside the mold. And the curing part was really, really different, actually. So coming back to a civil engineer, we usually cure structures using water. For refractory castables, we required heat. So actually, this cube was kept inside uh, this furnace, and the curing requires so many steps. The first step was heating it to 100 degrees Celsius for 1 hour, taking it out and keeping it in a muffled furnace at a temperature of 1100 degrees Celsius for about 2 hours, taking it out, keeping it at a temperature of 200 degrees for an hour or so, and then keeping it in room temperature for 1 hour to finish the whole curing. So that was a little different. After curing, we took the mold or the specimen, and we rolled it in an insulation that you see over here. It really tells you the practical situation which happens inside the furnace. Okay. The castable is sandwiched between two layers of insulation, as you saw in the first photograph. So we took this, we kept it inside the muffle furnace and applied the temperature loading of 1100 degrees for about 5 hours. For 5 hours, and then we took it out and kept it to the room temperature for the remainder of the day. 5 hours inside the oven, and the remainder of the day it is kept in the room temperature. So it's like a cycle, a temperature loading cycle. It is something which is similar in what happens in the field when the artisans burn the or melt the glass. They do it for 5 hours, and then the whole process stops for one day, and then the next day they do it again. So this cycle was done for 15 straight days, and the dimensional changes were observed, and it came out to be very good. The dimensional changes was really, really lesser compared to what we expected. So it was about 2%. The maximum value was 3%, which was given in the brochure. So actually, what we wanted to test out was whether it can withstand the harsh temperatures that it can be subjected to. So it came out really well. So the conclusion is like the furnace was consisting of 4 layers. The first layer or first and third layer was consisting of these insulation blankets. Second layer refractory castable concrete. Well, the fourth layer is just a housing kind of like an arrangement. It is based upon steel, and steel being a very good conductor was considered to be the fourth one. Not the first or second, it's the fourth one. And the materials for the castable and the castable as well as the insulation was selected using two parameters: refractoriness and PLC. and we did an analytical model of the same thing, and we found out it doesn't really require any amount of reinforcement. Very little amount of reinforcement was required, but we have to note that it was subjected to heat directly. In practical situations, we have the blanket or the insulation to protect it from the direct heat. So that is why we did not have any reinforcement for the castable concrete. Physical testing showed that it was very good enough to withstand harsh environments, and that was the thing which I wanted to say right now. If there is any doubts, I'll be really happy to talk to you about it. Thank you so much for your patience.
Okay, the layers,
Yes, sir.
right? The layers you have given, no? That first layer, second layer, third layer, no?
Yes, sir.
It is from inside or from outside? There
Inside.
inside only. You are coming from the heat zone to the layer you are coming.
Yes,
Okay.
yes.
Did you made any analysis by changing this material in the different layers? I mean the stacks. You did it only on software, right?
Sorry, sir. You did it only in?
You taken the experiment only on software, right?
Yes, sir. We have done it in a
Initially, right?
Yes, we have done it in StatPro.
Start Pro initially. Then
Yes,
in
sir.
that the arrangement, the first, second, third, did you change any the arrangement and you saw the any difference?
No, sir. It was actually we did not do it in layers, sir. This was
Hmm.
only the castable concrete which was subjected to the heat. We did not include the layers inside it. We just wanted to see how it behaves individually rather than the sandwiched way that we wanted to design. The worst case scenario, sir.
Okay, worst case
How it-
scenario. Okay. Then you analytically you did it. Practically
Yes,
you measured it. Huh? The
yes, a
temperature.
little testing also, sir. Yes, sir.
Okay. So what would be the temperature loss you have measured? How much percentage?
Temperature loss, sir.
Hmm.
Like from the outside to the
Inside. Hmm. From inside
actually
to
it
the
was
outside, right?
inside it was about 1300 degrees.
Hmm.
When it comes to the outside environment, it can be in the range of 40 to 50 degrees, sir.
40 to 50 degrees. Okay.
Because there's only some things which we can do. If we include it again, if we include another layer, then it will cost wise it won't be really feasible, sir. Because IIT gets their they
Sure.
do it for the welfare of these people, so they could not do much about another layer, sir. This was
Okay.
itself a very big layer, so
So
that's
this
why
four layer itself, it's a big one. Okay.
they are doing it practically in IIT, sir. They have built it and they're going to transport it to that Purampur, and they will be testing it again, sir. This is
Yeah.
one of the
Okay.
equations. Yes.
So because of the continuous the maintaining the temperature, you could able to take out the without joint bangles.
Yes, yes, yes. Jointless bangles. We have a video for that also, sir. Yes.
Okay. Okay. So any other questions from the audience? Any other question?
Any question from audience side? Okay, sir. Shall we move to the next
Okay.
next
Thank you. Thank
participant,
you,
sir?
Vignesh.
Thank you, sir. Thank you so much for listening, sir. Thank you.
Okay. Thank you.
Before going to the next participant, I want to welcome another chairperson, Dr. V. Vijayaramnath, as professor and head of Sairam Engineering College. Sir, kindly welcome to this. Sorry for delay.
Thank you, sir. Sir, Krishnamurthy sir, good morning, sir. Vijayaramnath, sir.
Morning, sir. Morning, sir. Good evening.
Sorry, sir. Due to network issue, unable to join, sir.
Okay, no problem, sir. No
Sir.
problem.
Thank you, sir. Thank you, sir.
Okay, next.
Sir, and the next participant is Radhika. Radhika,
Sir, sir, actually, Radhika is my co-author,
Radhika
and
is-
I am Vignesh. I am presenting behalf of her. That is statistical.
You are
analysis.
going to present in behalf of her.
Yeah, she's my co-author and guide, and I am
Mr.
I'm writing the paper. and she was my guide, so that I'm presenting the paper.
Okay, do you mean to say that you are also one of the authors?
Yes, sir. I'm also one of the authors.
Okay, then
I'm the main author, and
you can
my
proceed.
co-author.
Okay, you can proceed.
Then you can proceed.
Okay,
proceed.
okay. Okay, sir. Thanks so much. Sir, are you able to see, sir?
Yeah.
Presentation? Yes.
Okay.
Okay, sir.
Statistical analysis of process parameters in drilling SS41. Okay.
So, good afternoon all, and today I'm going to present one of my research topic, that is the statistical analysis of process parameters in drilling of SS410 stainless steel. And the main reason that I'm presenting this paper, or the main reason that I'm working for SS410 material, is that the main problem that we face in a day-to-day life is that we need to analyze the machinability nature, especially the drilling of SS410 stainless steel. The main reason we need to work for SS410 stainless steel the main reason we need to work for SS410 stainless steel, because the machinability condition and the condition for the working of that martensite stainless steel, that is SS410 material, is very difficult, and the machinability nature of that material is also difficult, and the many works are not done on behalf of the drilling process, and only very minute works are done on the other further machining operations, such as the turning and other further machining operations. So the main agenda of this work is to analyze the drilling process of SS410 stainless steel. The main objective that I bring forward to fulfill this statement is that I am correlating one of the main input parameters, or the main input parameters, such as the speed, feed, point angle, with the output response, such as the surface roughness, material removal rate, and ovality, which are a wide which have a very great influence on the material finish stage, and to obtain the maximum level, or to analyze the maximum, which one is the maximum optimized parameter value, which has a direct influence on that machining process. And the another thing that is a part of this research work is that I'm formulating a predictive model, that is like I'm forming a model that can predict the value of the output responses, such as the surface roughnesses, material removal rate, and ovality. And the experiment methodology that I've followed during this work is that the main thing that I'm followed in this work is that the initial one, that is the material selection, and as I mentioned earlier, since very less works are done in the SS410 material, and it has very wide applications in the field of automotive, marine industries, and all other forms, that is why the main reason that I selected the SS410 material. And the second one that I have done is the identifying the machining condition and the parameters. So as in a machining condition, since it is a drilling, and I have selected the input parameters, such as the speed, feed, and point angle, and we have the wide varieties of charts available, and with the help of that machining parameter charts, and also from another online research works, I have selected the certain set of parameters. Then for doing an optimization process, and for doing a better for getting an optimized result, I'm using a Taguchi L16 array for this work. And the second stage of the work consists of the blocking of that material, that is the input material, SS410 material, and then the grinding of the drill bit into the respective point angle. And the next set of the experiment level was of CNC drilling. I used a CNC BFW machine for the drilling operations, and the drilling was conducted on that machine, and the analysis were done after that. And the series of testing operations that I followed was the MRR calculation, ovality measurement, and the final DOE analysis and ANOVA analysis using the Minitab software. So these are all the main methodologies I have followed throughout the research works. So this slide, I'm briefly explaining what are all the importance of the SS410 material and why I choose that materials and why I choose the HSS drill bit for this work. So, as I mentioned earlier, it has very wide applications in the field of marine industries and also in other fields like automotive industries and also has the wide varieties of applications in the boat, screws and bush nuts, shafts, pumps, valves, etc. We need to analyze and how it is working and how the machinability nature of that material is and which are parameters are suitable and what is the trend of the parameters which can directly influence the machining properties. We also need to know all those factors for a perfect machining analysis or the perfect machining condition. And why drilling? Because the drilling has wide varieties of applications and very less works are done in the drilling operations. We know that the drilling is one of the most familiarized machining operation we can use in the automotive industries, marine industries and many other related industrial sectors. And why I used HSS drill bit? The main reason that I used HSS drill bit because it is very economically beneficial while using an HSS drill bit, and it is mainly used for drilling some of the hard materials, and it is somewhat resistant to heat form. And to make the machining operation more economical and more beneficial to the industrial areas, I have chosen the HSS drill bit and as my tool. So the machining conditions and parameters are explained in this slide, and as I mentioned earlier, the input parameters are the speed, feed and point angle, and the output responses are the surface roughness, opality and the material removal rate. And from the research work analyzed and from the online resources and from the material charts and from the machining charts, I have analyzed and I have selected the certain series of the parameters, and I have plotted and I have included that parameters into a Taguchi L16 chart that is like P3 L4 condition. These three parameters and level 4 conditions are applied for these machining operations, and this table will detailedly explain the 16 set of the experiments that I have conducted during my research work. So you can see that 16 set of experiments that I have followed with the different varieties of combinations of speed, feed and point angle. And by selecting the 16 varieties of formation, we'll get a detailed idea about which one is the optimized value and which one will be the better condition to get a maximum optimized machining end product. So these are all the experiment procedures I have followed. Initially, I have bought the in-code SS410 material. Then I blocked into respective dimension. Then I have grinded the tool, the drill tool, to the respective grinding tool point angle. Then I have done the CNC machining, then the CNC drilling. And since I have done the wet machining, that is the coolant was used during the machining operation. And this figure shows the final output, that is of 16 holes of the different machining condition. Then I have done the surface roughness testing, then ovality testing, and also done the material calculation. And after getting the result, the certain series of results for that 16 set of experiments, I have used an optimization technique using the Minitab software to get the final result. So these are all the important machines and its specifications that I have used in the research works. And the right side diagram shows the coolant specification, that the black socket 4000 strong coolant was used during the machining operation, since it is very feasible and it has very good stabilized property and low cost. And these are all the reasons why I choose the black socket 4000 strong, and it is mostly followed in the industrial point of view. And this is the result tables that I have calculated, that I have founded out with the help of the Minitab software. And you can see the 16 set of roughness value and the corresponding H/N ratio that I have obtained with the help of the Minitab software. And also the next stage, you can see the corresponding 16 set of validity and its respective H/N ratio. Then the final one, you can see the MRR and the corresponding H/N ratios. And each output parameter, such as the surface roughness, MRR and ovality, are analyzed separately. And from the Minitab software, we can get the plots, which really help to identify the optimized condition and also the trend of the parameters. So as in the objective, as I mentioned, I need to correlate the input parameters with output response. I need to analyze what is the trend of that parameters with respect to the response. So this S by N ratio will give the optimized condition. That S by N graph will give the optimized condition, and the mean graph will give the trend of the parameters. So you can see from the graph that is we need to follow a minimum a maximum S by N ratio condition so that it can really reduce, and it can reduce the external noise factors which we can reduce in the experimental procedure. The higher values of S by N, we can identify the control, the factor setting, and it will minimize the effect of the noise factors. So Taguchi analysis are used to minimize the effects of the uncontrollable factors or the noise factors. And this mean graph is generally used to analyze the trend or the how the trend of the parameters vary according to the output responses. So this graph, this mean graph will analyze, will help to identify the trend, and this S by N ratio graph will help to identify the optimized condition. So from that graph, we can identify that the experimental number 13, that is 16 speed and 0.05 speed and point angle 130 degree is the maximum optimized condition to get a better surface roughness, or the maximum surface roughness is obtained at that scenario, right? So the main thing is that I also plotted that the ANOVA table with that condition, and the ANOVA table, that is analysis of variance table, will help us to identify the significance of each parameters. And as you see the table, you can see the p-value is less than 0.05, so that all the three parameters are said to be significant, and we can clearly avoid the null hypothesis, that is the experimental errors are very much low. Since the p-values are less than 0.05, we can say that experimental errors are somewhat nearly less when we compare to the normal machining operation. And by seeing that percentage, we can analyze that which one is the most significant parameters out of the three parameters chosen. So the ANOVA results suggest that the feed is the most influenced parameters for the surface roughness, which is followed by speed and then the point angle. So the point angle is the least influenced parameters for the surface roughness. And the test ANOVA analysis was done at a 95% of confidence interval, and that is out of 100, the 95% of true mean values will obtain the true mean values throughout the operations. So after that, the Taguchi analysis, I have conducted a regression analysis also using the Minitab software. So the main reason for conducting the regression analysis is to get a prediction model, that is to get a prediction regression equation. So when we generate that regression equation, and when we do that regression, when we get that regression equation, and when we include, or when we use some values of speed, feed, and point angle, we can get the roughness value. We can predict the roughness value in the machining operation. So at what speed, so if we randomly take some speed, feed, and point angle, we can predict the roughness value. So that is what the main prediction thing we can get using this regression analysis and this prediction model. And the same procedures were followed for the ovality, and the S by N ratio will help to identify the optimized condition, and also the mean ratio will help us to identify the trend, and we'll get the different wide varieties of combinations. We'll get a combination of speed, feed, and point angle, which is the experiment number 1 is the most optimized condition for that out of that 16 set of experiment. And also using the ANOVA table, we can able to identify which one is the most significant parameter, and which one is the most influenced parameter, and which one is the least influenced parameters. And the same 95% of confidence interval was followed during the ANOVA analysis. And the regression analysis was also conducted during this experiment, and a regression equation was generated, so that we can form a regression. We can predict the ovality during when we apply some random values of speed, feed, and point angle. Then in the case of MRR, there is another output responses. We again followed the same procedures, and we'll get a maximum optimized value, and also we are able to identify the parameter strength. and we identify that the experimental number 16, which has the maximum, which is the maximum optimized condition for that following set of experiments. And from these also we can identify that out of the, while comparing the other two, in MRR the speed is the most significant parameters, and followed by the feed and the point angle. So these are all the analyses that are obtained during the by doing the ANOVA analysis, and also by doing the regression plot or regression analysis, we can get the predicted value of MRR by using some random values of speed, feed, and point angle. And the conclusion of this work is that I mentioned in this slide. So the surface roughness that is directly proportional with the feed and shows an inverse relationship with the speed and point angle. And ANOVA relieved that the speed has a major influence on surface roughness, which is followed by the speed and point angle. So as I mentioned earlier, it will help us to analyze the trend of the parameters with respect to the output responses, and also it will help to identify which one is the most influenced parameter and which one is the least influenced parameters. And in the case of MRR, the speed and feed is directly proportional, but the point angle is inversely proportional. And ANOVA revealed that the speed is the most significant. The speed has the highest significance on MRR, which is followed by the feed and point angle. And we can also conclude in the case of ovality, which is directly proportional to speed, feed, and point angle. And ANOVA revealed that the feed has the highest significance, and the point angle has the least significance on ovality. And also the prediction of the external responses is also possible with the help of this model. And all this analysis was done to analyze the prediction of the model and also analyze the trend of the parameters. So these are all the main reference papers I have. I just studied, or I just referred during my presentation. And thank you. And if you have any questions, you can.
Okay, Vignesh.
Yes, sir.
You said that if the point angle is more, surface roughness is reducing, right? For angle 130 degree, you get a good surface roughness.
Sir, for angle, yes, sir. The roughness will be more for more point angles.
Roughness will be more for the more point angle. Is it?
Yes, sir. The roughness will be the trend. The trend of the mean plot shows that by decreasing when the roughness will be decreased when we increase the point angle. Sorry.
That is what. So, what would be the cause for that? Can you analyze the cause for that?
The main thing is that when we increase the point angle, when we decrease the point angle, the line of action, that is the stress acting at the workpiece, will be more. So because of that stress acting, the stress concentration at the particular point will be increased, so that it will generate a heat. That is the point heat, and the stress concentration will be increased, and that heat will cause the wear. So that is why when we decrease the point angle, the surface roughness will be increased.
Because of the lower, I mean the acute angles.
Yes, sir.
For the obtuse angle, it will not.
Yes, sir. It is like the roughness will be less for when we increase the point angle, that is like 130 degree, so that the point of action, that is the stress concentration, will be distributed throughout that tool material end cutting angle, so that the temperature distribution will be also possible, and that stress concentration will reduce the
generally the point angle for the drilling is 120 degree. Is it?
Yes,
it's
sir.
the optimum angle.
Yes, sir.
If increase the point angle by 130 degree, what could be the other effects? That is, the machining time and other things. Did you understand anything on that? Did you studied anything on that?
Sir, actually, I have separate. I'm planning to study on that. Actually, I didn't work detail on that. I just want to. In this work, I have concentrated on the parameter strength and the analysis. Just the basic analysis and the parameter trend.
SS410. A lot of people have done the work. You have a lot many things. Anyhow,
Sir, actually, SS410 drilling works were comparatively very less, sir. Like in the CNC drilling was very less, but turning and other milling operations were done, sir. But the drilling works were very much less, sir. Actually.
Okay.
So I just need to analyze the condition of that drilling.
Fine.
So that is why I have worked for that.
Okay, fine. Any other questions from the audience?
Hello.
Yes.
Yes, sir.
Vignesh, I have one thing to ask about your ANOVA details on MRR and ovality. In that,
Okay, sir.
I could see that though error percentage contribution is not mentioned, other parameters error is significant. I think just wanted to know if error is more than any one of the parameters should be insignificant at 95% confidence level, but it is mentioned as significant. What is the reason, sir? Anything on that?
Sir, actually, the question was not clear. Can you please?
In your ANOVA analysis table for MRR and ovality,
Okay,
you
sir.
have mentioned all the parameters are significant. Okay.
Okay, sir.
At 95% confidence level.
Yes, sir.
But the percentage contribution you have mentioned, it is not summing up to 100, even though error is not mentioned there. But somewhere I saw that parameter 1 is around 26%, second one is at 36, and third one is at 15%. So if you add all those things and minus by 100%, what I find is that because error is coming more, any one of the parameters should be reported as insignificant. Did you
Sir,
get
actually, by doing that analysis, we get the exact values like this, and I don't think that the insignificant errors will be there in these conditions, sir, because it is what that done, and the suggestions were made according to that, and the conditions were chosen according to that. So.
Okay. Thank you.
Okay, sir. Sir, shall we move to the next?
Okay, Vignesh. Thank you very much.
Thank you so much, sir. Thank you so much.
Thank you.
Okay, sir. Next is Mystica. Is there?
Yes, sir. I'm here, sir.
Please present your topic in experimental investigation of cooling medium on submerged friction state process. AZ31 magnesium alloy. Please kindly present your presentation.
Is my PPT visible, sir?
Yeah.
So I'm Mystica. I'm a research scholar from CEG Anna University, and I'm here to present the topic on experimental investigation of cooling medium on submerged friction state processed AZ31 magnesium alloy. I have conducted this work along with Dr. Ratnasuryan sir and Shankar sir, and it was supervised by Dr. V.S. Sendilkumar sir from CEG Anna University. So the whole abstract of this work is that we have taken a magnesium alloy, which is AZ31, and we have conducted friction state processing by submerging this alloy in 3 different medium. The medium which we have chosen were water, cooling oil, and brine solution. Then we took these processed samples and analyzed the effect of these medium on the mechanical properties of these samples. And we have also altered the rotational speed and welding speed of this friction state processing. So friction state processing is nothing but a surface engineering technology. It's actually a surface treatment that is used to alter the grain structure of any material. So materials like magnesium, they have coarse grain structure, which is actually not as a disadvantage, and it's not allowing magnesium to be used in many other applications. So we have taken friction state processing to alter the grain structure of magnesium. We do this by actually taking a third body, which is nothing but a non-consumable tool. So in the friction stir processing machine, the non-consumable tool, it moves along the surface of this material. The material which we have chosen is AZ31 here. So the tool which rotates by itself and it moves transversely on the surface of this material. Because of this rotation, it causes plastic deformation by the stirring action. And because of this heavy rotation, there is a friction developing between the tool and the workpiece. Because of this friction, heavy heat is developed. And due to this plastic deformation along with this heat, the stir zone is developed in the material. So this stir zone is developed along with finer grains. A normal AC31 material has coarser grains. By using friction stir processing, we are developing a stir zone that converts this coarser grains in normal material into finer grains. So you can see the schematic layout of this friction stir processing here. So why do we need refined grain structure in any material? So we know that refined grain structure actually tends to improve the mechanical properties of any material. Basically ductility, if we take magnesium alloy, because magnesium alloys, as we know, are lightweight material, but their ductility is very poor. Ductility and formability of magnesium alloy is very poor. That hinders using magnesium alloy in many applications. So this friction stir processing here produces fine grains that improves the ductility of this magnesium alloy. So we have taken friction stir processing by submerging it in different medium. So why do we need submerging in friction stir processing? You see here, as I mentioned, as the tool moves, here stir zone is developed, but the heat developed because of the friction here is very excess. So this excess heat is sometimes dissipated away from the stir zone into this region. This is nothing but the heat affected zone. Because of this heat that is dissipated away from this zone, the grains in this region, they tend to be very coarse and they act as a point of crack initiation, causing premature failure of this material. So this is why we are submerging the friction stir processing setup inside some medium, so we can actually take away the heat that is being dissipated away from this region. So we can actually take away the heat that is coarsening the grains in this region. So when we take away the heat, we can also get finer grains in this region. That is the heat affected zone. We can reduce the size of the heat affected zone and we can actually refine the coarse grains in the heat affected zone. So this is why we are opting for submerged friction stir processing. So this submerged friction stir processing is nothing but submerging the whole setup inside a tank and filling the tank with whatever medium we choose. So we have done extensive literature survey. Here I have mentioned only a very few important takeaway points. So the Wu et al. In their paper talk about how magnesium is very lightweight and has high strength to weight ratio, and it has the capability to replace aluminium in many applications. But because of its poor formability and ductility, it could not. So we chose magnesium as a material for this study. Next, in the Douglas et al. In their paper, they talk about how submerged friction stir processing provides better grains than normal friction stir processing. And Basil et al. In their paper talk about how the submerged friction stir process reduces the peak temperature and the time exposed of this material to the peak temperature, thereby providing refined grains. And Liu et al. In their paper talk about reducing the size of the heat affected zone. There is nothing but reducing the softened region and developing finer grains. So the takeaway from the literature review was, first, as I told, we saw that the magnesium alloy needs to get improved ductility. So we chose magnesium alloy for this study. And we found out that submerged friction stir processing is better in producing better refined grains when compared to friction stir processing. So we went with submerging the friction stir processing setup. Next, we have seen that the coolants that have been chosen so far in submerged friction stir processing is only water, and they have not water, and sometimes they have chosen cryogenics, but they have not explored any other coolants. So we went with other coolants. Here we have used water to compare, and we have used brine solution and cooling oil. So this is the experimental setup of our study. Here you can see the FSP machine, and this is the tank which is made of plexiglass. The glass is actually leak proof, and we have used the medium of 5 liters for all the 3 mediums. And this is the tool we have used. The tool here is H13 steel. It's a non-consumable tool. And the shoulder diameter and the dimensions of the tool are mentioned here. And this is the parameter combination, which is very important for our study. We have taken 3 levels, the low level, middle level, and high level. The rotation, we have varied the rotational speed, transverse speed, and the 3 different mediums which we have chosen here or presented here. Then this is the first medium, which is water. The initial temperature was recorded as 30 degrees Celsius. Here you can see the second medium, which is nothing but the cooling oil. Cooling oil is nothing but the metal cutting oils which we normally use. We mixed it with water in the ratio of 1:10. Next, here you can see the third medium, which is nothing but the brine solution, which is nothing but 10% of NaCl mixed with water. So we conducted friction stir processing with all these 3 medium. We took the samples, conducted few other tests to analyze how these 3 mediums influence the mechanical properties of these samples. First, we studied the effect of these medium on the temperature developed during the process. Here you can see the chart. This is the low combination which I mentioned here in this table. So this is the first combination. This is the first combination. This is the second, and this is the third combination. So here you can see that the blue is the water. You can see water provides maximum temperature changes in all the combination. Temperature change is nothing but the change between the initial and the final temperature. So water provides maximum temperature change. This is because water possesses high specific heat capacity, that it can take away a large amount of heat for a large amount of time. This is why we found out that water could actually provide maximum temperature change. And you can also see here that the temperature change between water and brine is almost same in every parameter combination. This is because water and brine, they almost have same thermal conductivity, which is 0.4 watt per meter Kelvin. This is why they tend to have same temperature change. And the temperature recorded, which was very minimum, was obtained for cooling oil. This is because the thermal conductivity of cooling oil is very high when compared to water and brine. So this is the result we got for the effect of medium on temperature. Next, we analyzed the effect of these medium on different tensile properties. We went with ultimate strength and percentage elongation. You can see that the percentage elongation goes out for ductility, right? So the ductility obtained is very, very high for each and every parameter combination. For every parameter combination, the elongation obtained is very high when compared to the normal parent metal. So this actually proves that submerged friction stir processing of magnesium alloy improves the ductility, which was the main important objective of our study, because every combination produced better ductility. You can see that the ultimate strength is also maintained almost equal to the parent metal. This too is maintained simultaneously. This is mainly because of the ultra grain structure that is developed by exposing the magnesium alloy to friction stir processing while submerging into different mediums. Actually, the cooling oil, it produced better and maximum elongation and maximum ultimate strength. You can see it here. At the high parameter combination, the coolant oil produced maximum ultimate strength and maximum elongation. This, as I mentioned before, the coolant oil takes away more amount of heat, thereby actually reducing the size of the heat effector zone and also refining the grains farther and better than any other medium here. So the tensile properties tend to have better with cooling oil. Next, we found out the effect of these medium on hardness. We found out that the hardness kept on increasing with increase in the parameter combination. This happened with temperature also. Here you can see that with increase in the parameter combination, the temperature also kept on increasing. This is because with the increase in rotational speed, the tool tends to move very faster. So the frictional heat developed is also very high. Because of this, the temperature developed kept on increasing with increasing the rotational speed and welding speed. The same happens with hardness too. Here you can see again the coolant produced higher hardness for all the parameter combination. This is again attributed to the finer grain structure that is developed in the material. Because you see with finer grain structure, the hardness obtained is increases, as we know already. And with the parameter combination, the hardness also kept on increasing. And this is the microstructure SEM images that we got for different samples exposed to different medium. The base metal had an average grain size of 85.3 micrometer. As you can see, it's very coarse. but exposing to water and friction stir processing reduced the grain size to 5.43, which is a very significant change. And this is possible because of the plastic deformation and the heat produced, and also because of the cooling. The cooling, actually, with normal friction stir processing, you could reduce the grain size, but not to this amount. Only because of this cooling only we could obtain such significant decrease in the grain size. And with brine, the grain size further decreased to 4.51 micrometer. And with cooling oil, we almost got ultra refined grain structure. Here you can see how refined the grain structure is, and the grain size reduced to almost 2.3 micrometer. So the conclusion from our study is that these three different mediums, they provided different peak temperature. So depending upon the result you desire, you can use whichever medium you can need. And we saw that this medium, especially the cooling oil, had the tendency to maintain better tensile strength and ductility simultaneously, which is actually very hard when it comes to maintaining tensile strength and ductility simultaneously. This was achieved by using cooling oil. Then the hardness value was also obtained higher by using cooling oil. The hardness obtained was about 11% more than the hardness obtained under water medium. And the grain structure was also obtained was higher for the cooling medium, and the grain size reduced to about 71% less than the grain size using brine medium. So these are the conclusions from our study, and these are the few of the references we have used for our study. Thank you. Does anybody have any doubts?
Yes, the magnesium, how it react when you do the coolant?
Yes, sir.
The magnesium
Yes,
only that magnesium is a fire retardant, right?
So I can't hear you, sir.
Sorry, am I not audible?
Sir, yes, sir, I can hear you now, sir.
Okay, right. So this you have studied, no? That you concluded that the coolant oil is the better in mechanical properties. The coolant
So
oil
when compared to water and brine solution, we got better results with coolant oil, sir.
Okay, what could be the reason for that? Any idea?
So because the coolant oil tend to have more thermal conductivity and high specific heat capacity. So because of it, it could conduct away more heat when compared to brine solution in water. Since it conducted away more heat, the grain expansion reduced, and because of that, we found we got refined grains.
Okay. Wow. So what would be the temperature will produce during the friction stir in the machining of magnesium?
So magnesium, we got so the temperature changes were high, sir, but with normal friction stir processing and submerged friction stir processing, we got lesser only, sir.
Lesser means how much did you measured?
Yes, so we measured the difference in temperature only, sir, with thermocouples. We couldn't actually, it was difficult to measure because the material we took was only 6 mm, sir.
Okay.
So the placing the thermocouples were actually difficult. They fused with the material. So we could only measure the changes in temperature, sir.
Okay, any questions from audience? Any questions from audience?
Yes, sir.
Thank you, Vijay Ramnath.
So, you shown the effect of medium and other parameters. If you correlate between the parameters to parameters, then it will be a very good comparison for further proceeding.
So of different parameters, sir. Okay, sir.
A comparison between the parameters. You are comparing among that one. You are comparing between. Then it will give you a better solution.
Yes,
how
sir.
best you can perform the task.
Okay, sir.
Okay.
Yes, sir. Thank you, sir.
Thank you. Next.
Thank you, sir.
Yes, sir. Sir.
Chandrasekharan?
So Chandrasekhar sir is not there. I'm the author of the
Yes, sir.
another first author. I'll be presenting. Myself, D. Devarsidappa. I'm just sharing my screen, sir.
Fine, sir. Fine. Okay, sir. Okay, sir. Sure. Sure. Please.
Yeah, I'm sharing. Please wait, sir. Okay. And, is it visible, sir? Hello?
Yes.
Yeah. Thank you. At the outset, I'd like to thank the organizers of this international conference, Dr. Palni Kumar sir, and also the session chairs and both the session chairs and the session manager. Myself, D. Devarsidappa, a research scholar in Northeastern Regional Institute of Science and Technology, Arunachal Pradesh, presenting my research work on physiologic modeling of sustainable performance measures, and that is material removal rate during iridium of titanium alloy. This is the outline of presentation. Of course, it will be going through the introduction, brief literature review, the novelty of the present work, and then the experimental details, and then mainly basically the development of physiologic prediction model, results and discussion. We'll be concluding with conclusions and future scope of the work. As we know, wire electrical discharge machining is one of the very important advanced machining processes to machine electrically conductive materials with increased productivity and improved efficiency. With a iridium process, it is possible to produce integrate shapes in titanium, in any material for that matter, but basically it is preferred for titanium and nickel alloys, super alloys, which are considered to be considered as art to machine materials. Among the titanium alloy, titanium 6Al and 4V with 6% of aluminium and 4% of vanadium is popularly used titanium alloy. The titanium alloy components are used in varieties of engineering applications due to their high fracture toughness, superior anti-corrosion property, better welding characteristics, and enhanced specific strength. Material removal rate is one of the vital quality characteristics, and it is studied as one of the economic aspects of sustainability. The literature review on fuzzy logic modeling and application of fuzzy logic and artificial neural network modeling. These are the two important methods, soft computing techniques applied by the researchers to develop the prediction models. There are other analytical methods are also available. So Chakraborty and Das have developed fuzzy logic model to predict this.
Sorry to interrupt.
Yes, sir. Please.
Your PPT has not come.
PPT I have shared, sir.
No, sir.
Is it not visible?
No, sir. You have to double click that particular folder, sir. You just enter
it. Not open the file. He is showing only content.
You are showing only the content, but it's not opening the file.
No, it's.
You double click the file PPT.
Now, sir.
No, sir.
No, not
sir, you stop share, open your PPT, then share, sir.
Stop.
First you stop sharing, sir. Open the PPT, then you again share it, sir.
I've stopped to open the PPT. PPT, I have just okay.
Now you come out with the sharing, sir. You come out with the sharing.
Finding it difficult.
You click the stop share.
Okay.
Open PPT, then now share it. Then you can see it.
Open PPT. Now I have to share it.
Now open PPT in the background. Now share it. Then you can see it.
I have to share the screen or entire screen or window, sir?
The window, sir. Once you enter that one, you can see your PPT. Then double click the PPT. Then you can.
Okay. Now.
No, sir. Till now you did not share it.
Now it has come. Now it came, sir.
Visible.
Now it is visible, sir?
Yeah, it's visible.
Yes, sir.
Okay, let me go to the first one, sir. Then
No, not
introduction.
necessary. You just continue,
Okay,
sir.
I will
So you
continue with the
continue.
novelty of the
Where
I
did you
hope
stop?
it
You
is
continue.
visible.
Okay.
Okay, sir. In this work, basically, we have attempted to model the material removal rate as one of the response of YDM process during machining of titanium alloy. The novelty of the present work is that the machining equipment itself, that is the YDM setup, which uses reusable wire technology, which is seldom researched by the researchers. So in this case, we have considered 4 different process parameters: pulse on time, off time, current, and wire's drum speed. Actually, it is expressed in RPM. As I told you, the machine setup uses reusable molybdenum wire technology, which is less reported in the literature. And also, the modeling of MMR in YDM process using molybdenum wire is also less research. Machining setup and also response considered with the wire combination is also less research. Yeah, this is the wire set experimental setup. Experiments are conducted at BMS College of Engineering, Bangalore. Molybdenum wire of 0.18 mm diameter is used here. The 4 responses were varied at 4 different levels as per Taguchi L16 experimental plan. These are the experimental results obtained. As you can see, the maximum AMRR we obtained at the 9th experimental setup with 27 as pulse on time, microseconds, and then pulse of time 4 level, that this is the level 1, current at the level 3, and wire speed at the level, last level, nothing but the fourth level. This section describes the development of fuzzy logic model using fuzzy logic prediction model in YDM of titanium alloy. Fuzzy logic is one of the important soft computing methodology applied in diverse engineering applications and is found efficient. First proposed by Jihad, the fuzzy logic uses fuzzy set theory to derive the fuzzy rules. What is important here it is a very important and effective modeling tool which can handle the imprecise information in terms of linguistic variable, which is easy to understand and implement. In our work, we have implemented Mamdani type of fuzzy inference system consisting of 4 input variables and 1 output, and these are divided into different fuzzy sets depending upon their importance on the MRR. During ANOVA analysis, of course, it is not reported in this work. We found that current is the most influential parameter, hence we have divided this into 5 fuzzy sets, while the pulse of time is the second influential parameter. It was divided into 4, and the rest of the 2 are divided in 3 fuzzy sets. Total, the fuzzy rule base consists of 180 rules, and those are used in the fuzzy logic model, and it is implemented in MATLAB software using the fuzzy logic toolbox. Here, because we have 180 rules, we need to have the MRR values for those 180 data sets, and it is very difficult to conduct the experiment to obtain those data sets. The method here it is used is the prediction of MMR using the validated regression model, which is also taken from our published work. And this is the MRR regression model used to predict the MRR values for the 180 data sets. This is the methodology which is in line with the one which is used by Aburi and Dixit, in which they have used ANN predicted values of surface roughness to construct the rule base of fuzzy logic model in turning process. The same methodology we have used, but here we have used, instead of ANN, we have used the validated regression model. These are the this is the fudgified input and output variables considered in the study. You can see they all are clubbed together here. Pulse on time fudgified into 3, pulse of time into 4, current into 3, and then current into 5, and wire speed into 4 fudgy sets, whereas the MRR is divided into 9 fudgy sets to increase the accuracy and precision of prediction. This is the fuzzy rule base of the developed fuzzy logic model. The first rule reads as, if all the 4 parameters are low, then the MRR will also be very low. And here, the weight of the rule in construction of fuzzy logic model, we need to assign weight, but default researchers take the weight as 1 equal to unity. But here we have taken the membership grade of the MRR response variable as the weight, meaning to say that the statement of the truth value of the statement that the rule reads like this: if T on is low, T off is also low, and then current is also low and wire speed is also low, then the truth value of MRR being very low is 0.56, which is equal to the membership grade of the MRR value, predicted MRR value. Like that, we have correlated the different, means all the rules starting from 1 to 180, and some of the rules, the 10th rule, 50th and 150th rules are given here with the respective weights assigned to the rule. The next part is the result and discussion. To start with, the first is the validation of the fuzzy logic model. The developed fuzzy logic model is validated with 5 different data sets, which are, of course, these are not used in the development of the model, experimental values. As you can see, the fuzzy logic model predicted with better prediction accuracy. Error in the prediction, maximum error in the prediction was recorded as 7.69%, minimum as 1.54, average value is 5.44, and the model accuracy, which is taken as model accuracy based on this confirmation or validation data sets, is recorded as 94.5 to 95. And this is compared with our published work of regression model. We found that this fuzzy logic model prediction is better than the regression model prediction for the same data sets for the same MRR calculation. The second part of the results and discussion is the study of the surface plots FIS. This surface, the fuzzy logic modeling gives the option of drawing the surface plots for the entire rule basis. So we have taken the 2 important parameters, means pulse on time and pulse of time. As you can see that at higher values of pulse on time and the lower values of pulse of time results in higher MRR values. This can be attributed to high energy sparks produced due to longer duration. For more duration, the current is drawn during higher values of pulse on time, and at lower values, the faster flushing of molten material is possible, which results in higher MRR. And this shows the surface plot of MRR with respect to current and wire speed. As you can see, the variation of the MRR with respect to this wire speed is very slight, whereas a steep variation in MRR with respect to current is observed. As current increases, the high energy pulse are generated, that is imprints under the workpiece, that generate more heat and hence the temperature, thereby melting more material, that results in higher MRR. At higher value of current and wire speed found to result in higher MMR, as you can see from this plot. The contour plot is also studied. In this case, you can see that the darker region, this particular region, which is in the range of pulse on time in the range of 24 to 33, and also the pulse of time in the lower values of pulse of time, these are desirable, whereas the shallow values and the lighter section of the contour plots are not desirable, as they yield lower values of MMR, and darker regions indicate higher values as MMR. This observation, which we got through contour plot, is also supplemented with the previous surface plot. Similarly, another contour plot for wire speed and the current. Here also the darker regions are most desirable, as the MRR value at the darker regions is higher. The darker region on the left and these 2 corners. Accordingly, we can have the parameter combinations for the current is 3.6 to 4.4 amperes, whereas the wire speed is greater than 1370 RPM, is found suitable to obtain higher MRR. This can be therefore, it can be inferred that higher values of wire speed is desirable to achieve higher MRR due to higher cutting speed coupled with high current. As a result, more work material gets melted due to high pulse energy, and it is flushed off quickly due to by dielectric fluid, resulting in higher MRR. However, the values high pulse energy, the impinge on the surface will also create craters and voids on the machine surface, leading to poor surface quality. There has to be this has to be carefully selected. So, in general, it is expected that MRR to increase with the increase in the current. This is also due to the fact that at high level of current, the high and pulse on time, at a higher level of pulse on time and current, the discharge energy density is more, resulting in increasing the temperature of the workpiece, that in turn melts more material. That's the main reason for having higher MRR at higher level of current. This result presented here is also in agreement with some the researchers, Lee and others. This shows a SEM image of the titanium alloy obtained after the machining at the cutting condition corresponding to experiment number 9, which yielded highest MRR in the experiment conducted. As you can see that it is characterized by, there are two figures or two magnifications. At the higher magnification, we can see that the surface is characterized by some craters and also some cracks. That's the reason this can be attributed, the presence of cracks and craters can be attributed to high intensity spark impinge on the workpiece due to higher current. That is, the current level at this experimental setup was around 4 amperes, and then the duration for which the pulse remained on is also higher. Because of this, the pulse energy intensity is also more, that leads to cracks and craters on the machine surface, and that also result in higher surface quality will also be affected because of this. A similar type of observation is also reported by Furness and others during their YDM work on titanium alloy using uncoated brass wire. So that is the discussion part, and I'd like to conclude my presentation with these following conclusions. The fuzzy logic prediction model developed for prediction of MRR in YDM of titanium alloy was found accurate with average percentage error of 5.4%, and the maximum error is recorded as 7.69 with minimum error of 5.14. With model accuracy being close to 95%, the predictive performance of this model is also found better than the regression model as compared to the regression model of our published work. So based on the surface plot and the contour plot, higher levels of pulse on time in conjunction with the lower values of pulse of time result in higher MRR. This can be attributed to high energy spark produced due to longer duration for which the current is supplied and faster flushing of molten material by dielectric fluid as the duration between the two pulses is smaller. Continuing with the conclusions, the parameter ranges, parameter combination in respect of current and wire speed, here also higher values are desirable in order to get higher values of MRR as evident from both the surface plot as well as contour plot. Hence, it can be concluded that higher level of current and wire speed is desirable to achieve maximum MRR, and this is due to faster machining with high energy pulse, which melts the workpiece material, in turn giving higher value of material removal rate. In respect of the SEM surface morphology study, we have observed cracks and craters on the machine surface, and this is due to high intensity spark impinge on the workpiece for larger duration, drawing more current, that is also at higher value of current, is responsible for craters and cracks on the machine surface. So these are the concluding points from my research work. As an extended work of future, the fuzzy logic modeling, the similar type of methodology can be adapted to model other performance measures like surface roughness, power consumption, kerf width, etc. And similar prediction models can be developed using other soft computing techniques, and then the result can be compared with the present study. That's all from my side. Thank you very much for all the listeners If you have any queries, I would be happy to. Hello.
Any questions from audience size? Sir,
Hello,
sir?
Mr. Devasitarappa. Yes.
Yes, sir.
Thank you for your presentation, sir.
Thank
And
you, sir.
you, in the first logic, you have chosen some membership function, right?
Yes, sir.
You have chosen the triangular membership function.
Yes, sir.
Do you try with any other membership function?
Yes, sir. I tried with others also, bell-shaped and then trapezoidal also, but the result is not good, sir, with respect to those membership functions in my case.
Okay.
And I tried with different, by assigning different weights to the rules also, because by default, the weight is taken as 1.
Yeah.
I had other responses also, but it is not presented in this conference.
Yeah. Okay.
So that I have tried, sir. The result is good with only triangular membership function.
Okay, very good. That's what I wanted to know. That then the weight based on your experience, you are allotted 0.56.
A point, it's not, sir. Actually, weight is by default in most of the cases. The researchers take it as 1 equal to 1
Yeah,
value.
that is by default.
Yeah, default. But what I did is here, sir, instead of assigning weight equal to 1, we've taken the membership grade of the output variable as weight. Like in different cases, the weight value varies.
Okay.
Like in the first case, it is membership grade of MRR on this thing. Very low fudgy set is 0.56. The same is taken. In this case, the weight is coming as 1 in the rule 10. The rule 180 weight is coming as 0.8. So that is the logic behind taking this weight, sir.
Okay. Okay, sir. So anyhow, it is already published work with the regression model, right?
Yeah. The regression model result is published, and the result what we got through this fudgy logic is better than that regression. And that regression equation is used here to predict the MRR values for 180 data sets.
Okay. Now you are concluding that the higher current and the longer duration and the surface is also got damaged, right?
There are some cracks and voids, cracks and craters on the machine surface.
To avoid what we have to do? Do you find
this surface SEM image, a surface morphology presented is at experiment number 9.
Yes.
And this gives you the highest value of MRR. Like in the another experimental set is there where we have lowest value of surface roughness. In that case, it is this much of craters are not available. Okay. So depending upon the thing, we have to have a this selection, sir. That means optimization of process parameters is required, like considering all the responses, not only MRR, in considering the surface roughness and other
parameters. Okay.
Yeah, other parameter we need to optimize, and there we have to study the surface morphology.
Okay. Thank you. Thanks for your presentation. Is good. Right. Next, anybody? Sir, anybody?
No, sir. No problem. No, sir. No.
Okay, sir.
Okay, sir. Thank you. Yeah, please.
Okay, sir. Thank you, sir.
Okay, sir. Thank you. I'm stopping presentation.
Thank you. The next, Mr. Mayan Gupta is there. Mr. Mayan Gupta is there. Okay, I think it's not available. Next, Surya Vamsi. Not available. Mr. Elango Natarajan. So could you hear me? Sir, could you hear me?
Yes, sir. I could be able to hear. Only Ilango Ishwaran is there.
Ilango
Ishwaran. And
shall I call him, sir?
Ilango Ishwaran? He is under muting.
Yes, sir.
Okay, sir.
Yes, sir. So, shall I present my...
Sure, sir. You can share your screen.
Okay, thank you. So is it visible, sir?
Yes, sir. So you can.
Okay. Okay, sir. Thank you, sir. So good afternoon to all, sir. So my research topic is optimization of operational parameter in aluminum 5052 SS316 explosive cladding. Overview, introduction, objective, explosive cladding, experimental condition, discussion, and conclusion. Application of explosive cladding are chemical process vessels, marine applications, tube welding and plugging, pipeline welding, electrical applications, transition joint, pressure vessels, heat exchanger tube seats, attached cooling fins, military application, etc. Explosive cladding. Explosive cladding, a solid-state autogeneous metal joining technique, employs an explosive force to craft an electron-sharing metallurgical bond between the dissimilar metals. Controlled energy of a detonating explosive is used to create a metallurgical bond between two or more similar or dissimilar metals. As the explosion is initiated, flare plate is accelerated by the detonation pressure and flies at a very high velocity towards parent plate. Quality of explosively produced weld preliminary depends on the state of the interface between the participant metal and alloy. The objective of the study is to explosively clad aluminum 5052 SS316 clad metals with and without interlayer to develop a mathematical model for predicting the strength of the clad to determine the optimal condition through a response service methodology, that is RSM, to determine the tensile strength of the explosive clad. The explosive cladding. In this process, a piece of metal is made to strike another under heavy impact force. Under very heavy impact, and the clad between them is achieved. A joining of large sized component of difficult to weld metal are cladded by explosive cladding. When the electrical detonator was detonated, the potential energy stored in the chemical explosive is instantaneously converted into gas, which propagates a shock wave in the flare plate. This leads to an oblique movement of flare plate colliding onto the base plate and the generation of shock compression gas between the plates. During the collision with the base plate, the kinetic energy of the flare plate is converted into thermal energy. The energy spent at the interface determines the degree of plasticity at the interface and thereby influence the characteristic interfacial undulation. In explosive cladding, the detonation of chemical explosive forces the flare plate to collide the base plate to craft a metallurgical strong joint in a very short duration of time. And explosive cladding is associated with a number of parameters that influence the mechanical strength and the weld zone. The factors influencing the explosive cladding process are explosive standoff distance, explosive loading ratio, inclination angle, collision angle, detonation velocity, thickness of the flare plate velocity. So this is the base plate and this is called flare plate. There are two types of explosive arrangement, that is parallel configuration and inclined configuration. In the parallel configuration, the flare plate and the base plates are parallel to each other, but in inclined configuration, the flare plates make an angle, a particular angle with the base plate. The standard distance is the distance between the flare plate and the base plate. And this explosive loading ratio is the ratio between the mass of the explosive to mass of the flare plate. And inclination angle is the angle between the flare plate and the base plate. Explosive cladding with the interlayer. Explosive cladding is bonding process in which the energy released from the detonating chemical explosive is employed to create a metallurgical bond between two or more dissimilar metals. On detonation, the potential energy stored in the chemical explosive is converted instantaneously, that is below 50 microseconds, into kinetic energy due to movement of layer plate. The amount of kinetic energy spent at the interface dictate the formation of smooth wave interface. As the process is very rapid, that is within few microseconds, the judicial selection of process parameters, that is loading ratio, standard distance, property of explosive and the flare plate, etc., dictates the kinetic energy spent at the interface and restrict the intermetallic compound formed. Okamoto et al. Emphasized the significance of kinetic energy spent at the interface and deduced an empirical relation which depends largely on the flare plate velocity and the mass of the partition metal. And also the Tamil Chelvan et al., while cladding titanium steel, concluded that the formation of the determinal intermetallic compound is imminent when the kinetic energy spent at the interface is high during the conventional two-layer cladding, that is without interlayer. Alternatively, a strong clad devoid of intermetallic compound between the interface is achieved by employing an interlayer between the flyer and the base plate, which reduces the kinetic energy dissipation and increases the heat transfer area and also overall weldability. Here, this is the interlayer placed in between the flyer and the base plate. The experimental setup. The inclined explosive cladding configuration was attempted in this study. The aluminum plate as a flare plate of AL5052 with the dimension of 50 into 150 into 2, 150 into 2 mm cube, and the base plate of SS316. The same dimension are chosen as flare and the base plate. And the interlayer, there are three interlayers introduced in this studies: copper, pure aluminum, and SS. The same dimension with a 0.2 mm thickness is introduced in between the flare and the base plate. The distance between the flare and the interlayer, interlayer and the base plate are varied from 6 mm to 10 mm, which allow the flare plate to reach its terminal velocity. Similarly, the inclination angle, that is the angle between the flare plate and the base plate, varied 6 degree, 8 degree, and 10 degree respectively. A buffer, this one, a buffer plate is placed in above the interlayer. Above the flare plate to protect the flare plate from damage during the explosive process. The explosive was packed above the buffer plate, and the detonator was placed at one corner of the explosive pack. These are the photographic view of the experimentation. The photograph shows the experimentation before explosive cladding, during explosive cladding, and these are the photograph view of the explosive clad. The next one is in explosive cladding, the interface strength. In explosive cladding, the interface strength and the characteristics are dictated by the optimal selection of operational parameter via a standoff distance, loading ratio, inclination angle, and the interlayer. The optimal selection of process parameter results in a higher tensile strength. However, the strength will be reduced if the operational parameters were not selected properly. To aid the selection of operational parameters, various researchers developed two-dimensional numerical models, design of experiments, mathematical model, and the weldability window. Recognized adopted a response service methodology, that is RSM, to evaluate the tensile and the shear property of copper low carbon steel explosive clad. Similarly, Tricaria et al. Evaluate the length of the intermetallic layer, micro hardness, and shear properties by regression equation, while cladding aluminum and steel. In a different way, Tamilselvan et al. Employed a full factorial design of experiment to measure the different dimensions of interfacial undulation in titanium and steel 304 cladding. But studies on developing a mathematical model to predict the tensile strength of aluminum 5052 and SS316 explosive cladding with a different interlayer using RSM is scarce, hence it is attempted herein. In this study, the contribution of operational parameters, that is standoff distance, loading ratio, inclination angle, and interlayer enhance our interlayer enhance the tensile strength was presented. In addition, the regression equation developed using the ANOVA technique. Response surface methodology with the 4-factor 3-level orthogonal array design was selected and the experiment conducted as per the standard orthogonal array. The 4 parameters chosen as standard distance, loading ratio, preset angle, that is inclination angle, and interlayer with the 3 levels. And the next one. This slide shows the consolidate round tensile strength of different interlayer. Of different interlayered aluminum steel explosive clad corresponding to experimental condition. As per the whole 4-factor 3-level orthogonal array, we are conducting 30 experiments, 60 experiments. Sorry, so this is not visible. Okay. A maximum. This is a tablet in these 2 slides. Maximum tensile strength, that is 278 megapascal, is obtained for experiment number 30. With the parameters of standard distance 10 mm, loading ratio 1, and the inclination angle 10 degree with the SS 304 interlayer. Meanwhile, at the same time, the minimum strength was obtained 273 megapascal for the experiment number 17 with a parameter of standard distance 10 mm, loading ratio 0.6, and inclination angle 6 mm with the aluminum interlayer. However, the minimum strength of the clad is 20% higher than the weaker base alloy of aluminum 5052, that is 180 megapascal. So this slide shows the microstructural characteristics of the aluminum 5052 SS316 clad with a different interlayer, a different parameter. So all the picture shows this microstructure analysis shows the interface as divide of intermetallic compound and a trapped jet and crack and other defect. This is due to the proper selection of the process parameter for the experimentation. However, the test of significance of the parameter is tabulated here. It is witnessed that all the chosen parameters holds here.
Sir, quickly conclude, sir. Quickly conclude.
Okay, sir. Okay. Yes, sir. 5 minutes. It is witnessed that all the chosen parameters holds a significant effect on the response respect the square of the SS and interlayer and the interaction effect of standoff distance and interlayer and loading ratio and inclination angle. The p-value, this one, and the p-value for the regression model is lower than the 0.05, that is 95% confidence, which indicates the statistical significance of the development model. The correlation coefficient R square was 97.76, that indicate 97.76 of the variants are considered in the regression model. This regression analysis of the operation parameters for copper SS 304 aluminum interval layer are shown in this figure. The normal probability plot shows that the residuals of the tensile strength fall near the value of developed equation, that is straight line, and the normal distribution of the error is inferred. Hence, it is concluded that the developed regression model is integral with the experimental value. Then next one, the surface plot shows all the for different parameter, the loading ratio and inclination angle and the standoff distance and inclination angle, standard distance, loading ratio. So all the three parameters are increases with while increasing all the three parameters, the tensile strength also increases. The optimum results for a tensile strength. The desirability of the optimum is closer to 1, that is 0.92, that is 9255, which indicates that the range of operation parameters is within the working range. The confirmation experiment shows the confirmation experiment with the optimum parameter settings and the corresponding tensile strength is shown in table. The predicted response is very close to the experimental results, and the error is less than 3%. That is, the error is only 2.14%. Finally, the conclusion part is the developed relationship can be effectively used to predict the tensile strength of dissimilar explosive clad. As the deviation is less than 3%, the optimal level of tensile strength for the 95% interval is predicted. The operational parameters, standoff distance, loading ratio, inclination angle are significantly influencing the RAM tensile strength of aluminum 5052 SS316 explosive clad. The response tensile strength is directly proportional to the standoff distance, loading ratio, and the inclination angle. These are really some references.
Okay, sir. See, the explosive, what is the kind of explosive you have chosen for this purpose?
So, Geo 90, Sun 90, the explosives. So that
the same quantity of explosive have been used for all the three kind of experiments.
Same explosive, but different mass weight ratio, L by R, loading ratio.
Then how did you decide that? L by D loading ratio you have decided, but when you choose the quantity for aluminum and steel, copper and steel, and other things, you vary it, right?
Yes, sir.
If the copper, if the quantity is more with the aluminum, what will happen? That's what.
If the explosive radius is more, what is the? It will the more due to more detonation, the material spoiled, sir. There is no well.
How did you control that? How did you control
that is depending on the literature survey, sir. By using the literature survey, we are choosing the range. The explosive and also the detonation velocity of the explosive is 4,000 meter per second, sir. Depending upon the explosive velocity of the explosive and the mass ratio, we have to choose and the literature review.
Based on the literature survey, you choose it.
Yes.
About those things, you are not talked anything on this. So that's it. Okay. Thank you very much, sir. Thank you. Your presentation.
Thank you, sir. Thank you, sir.
Hello. Sir, next. Can you go to the next participant, sir?
Oh, next, Devasiddharabha, you want to talk anything? You want to ask any question?
Sir, yeah. Iswaran, sir.
Yes, sir.
Hello.
Yes, sir.
Sir, what is the design of experiments or experimental plan you have used? Yeah, 60 experiments you conducted. What is the
4-factor 3-level orthogonal array we are choosing, sir.
Your model is regression model or RSA model, sir?
RSM model, sir.
And then the experimental plan you have used, 60 experiments based on what type of design? So like RSM is
RSM,
based
sir.
on BBD design and CCT design are mainly followed.
RSM based on the RSM, sir.
Yeah, I got it. But RSM is a methodology that experiments are obtained as per the design, BBD design, box backend design, or central composite design. Just I wanted to know which design you have, which experimental plan you have used.
Central composite design.
CCD.
CCD design you have used.
Yes, sir. Yes, sir.
Yeah, that was not mentioned, but no, that's why. And somewhere I saw that it is mentioned as regression. That's why I got confused whether it's a regression model or RSM model, response surface model.
Regression equation we are getting that. That's why. Okay, sir.
Okay,
Sir.
the
Thank
model
you.
you got.
Okay,
Okay, sir. Thank you very much.
Okay, sir. Thank you, sir. Sir, Mr. Lakshmi Narayan, sir, are you in line, sir? Lakshmi Narayan, sir?
Hello. Yeah, sir. Can you hear me?
Yeah, I'm hearing you, sir. You can present, sir.
Yeah. Thank you, sir. I will share my screen. Sir, is my screen visible, sir?
No, sir, not visible, sir.
No, sir, you are not shared till now.
I have not shared it. Just a minute. The option share screen.
Once you shared, it shows that Lakshmi Narayan sharing. Like that, some display will be.
Yeah. Visible, sir? Hello?
Okay, sir.
Is it visible, sir? Shall I carry? Yeah. Good evening, everyone. The chairperson as well as the organizing committee. Thanks for giving an opportunity to present my paper, which deals with the micromechanical and experimental analysis of thermal conductivity of hemp Palmyra reinforced hybrid composites. I am the corresponding author, and along with me, the other two authors, one of my guide, Dr. Bhaskar Rao, and the other one is Shiv Bhaskar Rao, who is my fellow colleague. And with this, I'll proceed further to give a bit part of introduction regarding the work what I have taken. Normally, we see that natural fibers are mainly used because of the low cost as well as easily available. But nowadays, even these single reinforcements are getting replaced by double reinforcements or a double matrix, what we generally term it as a hybrid composite. So these hybrid composites are gaining much significance in order to meet various novel design requirements, both the way of economy as well as the effectiveness of working of that particular material. So there is a gravity of the situation where we need to find out the thermal behavior, because basically why I have chosen this part of application of thermal behavior is my objective is to work with the insulation of buildings in order to provide like that. That's why I have taken this thermal behavior of the hybrid fiber reinforced composites. We have gone through the literature and it has predicted majority has worked not only with the experimentation, what are the experimental work that has been carried is being compared with the available analytical models as well as the finite element analysis. So coming to the overall objective of this work, our objective is to predict the thermal conductivity of hemp Palmyra hybrid natural fiber reinforced epoxy composites. So this particular diagram represents what is the flow chart for the preparation, what are the basic properties for any type of a polymer matrix composite. It starts with the statistical mechanical properties for the and at the third or the fourth box, we are working on the thermal properties of the hybrid fiber reinforced polymer matrix composites. We can also proceed for the water absorption, tribological, and finally what is the application. Similarly, coming here, this only represents what are the different classification of the fibers which are both natural and synthetic. In here, whatever the selected fiber, one is hemp, the other one is a Palmyra, which is also termed as oil palm. One becomes a batch fiber, that is.
Sir, sorry for interruption.
Yes, sir.
Sir, Lakshmi Narayan, sir.
Yeah, sir.
Sorry for it is getting late. You can directly go to your fabrication part and analysis part, sir.
Yeah, you're right.
Thank you,
Okay.
thank you, thank you.
Yeah. So these are the materials that I have selected. One is the epoxy, the other one is the hardener. So the hardener and the epoxy are mixed at a ratio of 10:1. And the reinforcement, one and hemp, and the other one is the palmyra. And the fabrication method is a simple hand layup technique. I hope I can also skip this. Why I have selected hemp fiber and what is the need of selecting both these fibers? Whatever underlined in the red color. One is to go with the assortment of the building materials. And one of the most important property is the best ratio of heat capacity of all fibers, giving it superior insulation properties. That is why hemp is selected here. And also hemp is possessing a thermal conductivity of 0.048 watt per meter Kelvin. Similarly, coming to the case of palmyra also, it has a good resistance to heat and mostly it is chemically resistant type of a fiber, which possesses a thermal conductivity of 0.1 watt per meter Kelvin. And whatever the epoxy I have selected, that is LY546, also possesses a thermal conductivity of 0.363 watt per meter Kelvin. So these are some of the tensile properties. Coming to the fabrication of the specimens, actually we have fabricated 13 specimens, out of which the first specimen will be a pure matrix, 100% epoxy, and the remaining 12 specimens are fabricated with respect to a related fiber ratio of 1:1, 1:2, and 2:1 with the different weight percentages from 10% to 20, 30, and 40%. That's what the total site that represents. And these are manufactured and type of time what we have gone for the curing procedure is at most the time what we have consumed is 2 days, that is 48 hours. And in order to conduct the thermal conductivity test, we have specimens as per the standard of ASTM E1530, where we prepare a circular disc type specimens where it is conducted on a thermo machine that will provide us what is the value of the thermal conductivity. So here you can observe what is the specimen preparation. This is the micromechanics and macromechanics. And most importantly, the paper concentrates on the generation of a micromechanical model, which is most importantly, rather than going along with the experimentation, we have generated a mathematical model which gives a clear identification in order to go for the comparison with the experimentation. Similarly, we also analyzed with the existing analytical model. So coming to the case of the results and discussion, we have conducted the test for both the only the transverse thermal conductivity, have not done it the longitudinal. So after going through all the procedure of the experimentation, it is clear that the longitudinal thermal conductivity at a weight percentage of 40 fiber loading, we have observed 0.239, 0.244, and 0.232 watt per meter Kelvin at the relative ratios of 1:1, 1:2, and 2:1. Similarly, we have compared what is the error percentage. Somehow, while evaluating the error percentage with rule of hybrid mixtures, in case of transverse thermal conductivity, we have observed a long deviation. So I will also give what is the reason for that. So this is the table that gives us a clarity of what is the relation or what is the comparative statement for the error percentage. The first column represents the experimental value. The next one is the finite element analysis. The next one is the rule of hybrid mixtures. Next, we use the Halpin-Tsai model and Lewis and Nielsen model. So out of which, at a weight of low thermal conductivity being observed 0.232. Similarly, in case of transverse thermal conductivity also, we observed at the same fiber loading percentage of 40, which is given as 0.226 watt per meter Kelvin. So right from both the results clearly that the conductivity decreases 77.7% in case of transverse thermal conductivity, and similarly around 36.08 while evaluating along the longitudinal direction, that is along the parallel to the pipe. Similarly, the FEA model, the results we can see here. The first EA diagram represents the longitudinal direction, the other one is the transverse direction. So at most, rather than at the edge of the specimen or the laminate, the mid part of the laminate is providing a good result. So that's why FEA is very much in line with the experimental results as well as the mathematical models what we have generated. So finally, I like to conclude that we have generated a new mathematical model to predict the transverse thermal conductivity of the selected hybrid fiber reinforced composite. And as previously conveyed, the longitudinal and transverse thermal conductivities of this composite has decreased by 36.08 and 37.74 at a maximum fiber loading. And finally, the experimental results are in line with the other analytical models as well as the FEA models. But I want to share one important thing. There is a problem at this particular table. The rule of hybrid mixtures, the experimental values and the percentage of error what we are observing here in case of transverse thermal conductivity is very much greater. This is somehow not even greater, what can I say, not an acceptable. The only reason is, as the rule of hybrid mixture follows a upper bound and a lower bound, and in the transverse direction, we evaluate the property by using inverse law of mixtures. We evaluate like that. So we will be following, having a deviation from the required set of values. In future, we want to also proceed further by providing alkaline treatment to the fibers and once again recheck for the values of this thermal conductivity, whether it may get lower than the obtained values from the case of non-alkaline treated fibers. Thank you for giving this opportunity. If any questions, I'll be happy to respond to this. Please.
Yeah, thank you. Thank you, Ramesh sir. Vijay Ramana sir, Krishnamurthy sir.
Good evening, sir.
Yeah, good evening. Any questions in the interview? Krishnamurthy sir, any questions, sir?
Yes, sir. Lakshminarayana.
Yeah.
This layers, how many layers do you have it? So this layers,
Six
no?
layers, sir. 6 layers.
Only 6 layers.
Yeah.
Okay. For all the 13 experiments, you have 6 layers.
Yeah, we have taken only 6 layers.
6 layers.
Yeah.
So only the rule of, the variation, only the weight and the resin weight, only you are changing it.
Yeah, we are changing the reinforcement ratio as well as the relative ratios of both the fibers, sir.
Both the fibers.
You can see here, 5% hemp and here 5% palmyra.
Okay.
That is 1:1. That is 1:1. While coming to the C6 specimen, we will see that hemp is 3.3, whereas palmyra is 6.7. That becomes 1:1.
Okay. Then the temperature in the experimental values, how did you measure the temperature?
Actually, the thermal conductivity apparatus is available at Siddhartha Engineering College near to our college, sir. So we went there and we have tested the specimens.
Okay, sir.
Yeah. Thank you, sir. Thank you, sir. Dr. Vijay Ramana sir, any questions?
No, sir. No questions, sir.
Okay. Thank you, sir. Thank you very much. Thank you, Lakshmi Narayana sir. Very good work.
Yeah. Thank you very much. Yeah, sir.
Yeah, thank you very much. Yeah, I think Krishnamurthy sir already closed. I think all the
I
presented.
Yeah. Okay.
Thank you for your chairpersons. Yeah, they were the person.
Yes,
you are going,
sir.
You are going to present.
He's already presented.
Presentation is over, sir. In the schedule, by default, my corresponding author name is reflected. So as I am presenting, I request you to issue the letter in my name.
Okay, sir. No issue.
And please note that.
And in our conference website, your feedback link is there. You have to enter your feedback on both your correspondent author and also your name. Okay. You both of you get a certificate. No issue.
Okay, sir. Thank you.
Okay. Thank you very much. Thank you. All the best. Okay. Thank you, sir. Yeah. Thank you, sir. Thank you for our chairpersons, Dr. A. Krishnamurthy sir and Dr. B. Vijayaraman sir, HOD Mechanical Sairam Engineering College. And Krishnamurthy sir, I think a lot of questions you are asking on the on the participant side. They are very much keen about your presence, and they are triggering about their work, and they have to rectify, and also they have to correct all the things. That is a motto.
Sir gave a lot of inputs for the students to further do more research.
இல்ல ஒருத்தர் கால் பண்ணி சொல்லிட்டாரு சார், என்ன சார் அவ்வளவு क्वेश्चन கேக்குறாங்க சார் அப்படி சொல்லிட்டாரு. நாங்க ஜஸ்ட் ஃபார் ஃபார்மாலிட்டி நினைச்சோம் சார், ஆனா நீங்க நல்ல ப்ராப்பராவே பண்றீங்க சார் அப்படி சொல்லிட்டாரு. ஓகே, thank you sir, thank you.
It is our duty, sir. It is our duty as senior people. We have to guide them, right? We have to mold.
Yes sir, yes sir. Thank you very much sir. Thank you sir.
Thank you sir.
Thank you.
Thank you sir. Thank you sir.
Thank you sir. Thank you.
Happy to see you sir.
Thank you sir. Happy sir.
Thank you.
Thank you Vijayaraman. Thank you.
Lakshmi, best of luck sir.
Yeah, thank you, sir. Thank you very much. Really, I am very much thankful for your organized committee during this pandemic. Still, you organized in a very well manner. Thank you, sir.
Yeah, thank you very much. We will publish your paper very soon. Okay, no issue.
Yeah, thank you very much.
Okay.
Thank you, sir. Close the meeting.
Yeah. Okay.
Anything there?
No, sir. It's already over. Thank you.
Okay. Shall I leave the meeting?
Yeah, yes, sir. Thank you, sir.
எப்படி மீட்டிங் வெளியில் வரணும்?